In this problem, as shown in the figure, a uniform rod O dash of length L is hinged at the point O. It is hinged at the point O. So it is oscillating about this point. So as it is oscillating about this point, it is the axis of rotation. Held in a place vertical between two walls having two massless springs and having same spring constant. The springs are connected at the mid and the top end of the rod as shown in figure 1, and the rod is made to oscillate by a small angular displacement. Then the frequency of oscillation of the rod is F1. On the other hand, if both the springs are connected at the middle of the rod as shown in figure 2, the rod is made oscillate a small angular displacement, then the frequency of the oscillation of F2. Ignoring gravity and assuming motion only in the plane of the diagram, only motion is in the plane of the diagram, the value of F1 by F2 is. So both the cases, so parallelly we discuss. So let us take the first case. So in the first case, two walls are there. These are two walls. At O, a rod is hinged. So this is the axis of rotation. This is axis of rotation because it is hinged. This is O dash. So first of all, let us take this spring. Right. If we displace the rod through a small angular displacement theta, then this is at the midpoint. Then immediately what happens, whenever we displace through some small angular displacement theta, immediately this, let us take the spring constant is K. So immediately restoring force will act in the opposite direction. What is the restoring force in the spring here? That is F. F1 I will say. This is of the first spring. So whenever force acts in this direction, it will turn back. So from there, from the point of application of force to a perpendicular distance from the axis of rotation is L by 2. This is L by 2 because it is fixed at the middle, L by 2. So whenever we displace through theta angle, so what we know, whenever we displaced this theta, this is length L, this linear displacement will be x is equal to L theta. Actually, it is a sector formula you might have known. This is theta, this is r, this is s is equal to r theta. This formula I am using here. So here the linear displacement, this one I will take it as x. This I will take as x. Okay. Then whenever I made a small angular displacement of the rod, immediately restoring force develops in a spring. That formula is minus kx. So x value is minus k. This x value is L by 2 into theta. L by 2 into theta. This is the force. Then it is moving here and it is oscillating. So axis of rotation is at O. So about this axis of rotation, the torque of the rod is equal to force into perpendicular distance between the point of application of force to the axis of rotation, that is L by 2. So F1 is equal to how much? minus k L by 2 into theta into L by 2. So tau 1 is equal to minus k L into L square theta by 4. This is tau due to first spring. Next spring. In the same diagram, these are the walls. This is the rod hinged at O. So this becomes axis of rotation. The length of the rod is L. So at the top, spring is fixed. This is spring 2. This spring constant also K. If I make a small angular displacement theta, then this is x dash. So immediately what happens in the spring? Restoring force will act, that is F2. So F2 is equal to minus K x dash. What is that x dash? This distance is L into theta. L theta x dash is equal to L theta. Now let us calculate the torque. Tau 2 is equal to F2 into perpendicular distance from the axis of rotation is L only. So into L. This is the formula for the torque. So it becomes minus K L theta into L. So tau 2 is equal to minus K L square theta. This is equation 2. But what happened here in picture 2? Let us revisit the diagram. In figure 1, both springs are connected to the rod. So when it is oscillating, effect due to first spring, effect due to second spring, both will take place. That's why net torque acting on the rod is equal to I alpha. Tau is equal to I alpha formula I am using. Here one more formula, let us try to remember. What is that formula? Whenever a rod is oscillating about an axis of rotation at the edge of the rod, then moment of inertia formula is ml square by 3. That formula I will use here. So what is net tau? The torque due to first spring, torque due to second spring is equal to, this is hinged at the edge of a rod. So at one end of the rod is oscillating. So this formula is ml, length of the rod is L, mass of the rod is m, ml square by 3 into alpha. So tau 1, tau 2 is equal to, see, tau 1 is equal to, see, I will show you. This is minus k L square theta minus k L square theta by 4. This is minus k L square theta minus k L square theta is equal to ml square by 3 into alpha. Right? So now what I do? ml square by 3 into alpha is equal to minus, I will take common KL square theta, KL square theta, then 1 by 4 plus 1. So here L square cancels. So alpha is equal to See here, theta will be there, minus k will be there. So minus k, this is 5 by 4. This 3 comes here and m goes there here, and this is theta. Right? So alpha is equal to minus 5 3s are 15k by m 4m into theta. This is equation 3. So standard formula for SHM we know na, when a body is simple harmonic oscillator, alpha is equal to minus omega square theta. So on comparing these two equations, I will get omega 1 is equal to, because this is a figure 1, is equal to root of, this is 15k by 4m. This is equation 4. Now let us go for the second one. Second diagram. Second diagram is like this. I will draw a line here. Second diagram is like this. These are the walls. Yes. Second diagram is like this. These are the walls. This is the rod. Here, when you look into the diagram, figure 2, both springs are at the middle. They are connected in either way, here and here. Then what the other formula we can remember here? When the springs are connected like this, both are having spring constant K. These two springs are in parallel. So springs in parallel formula K1 plus K2. This is also K, this is also K. So 2K. So these two springs I can make into one. So this concept I will apply here. So both the springs now became one only, and the K is 2K. That's all. Right? This figure 2 is simplified like this. This is nothing but parallel connection of two springs. So if I made a small angular displacement here, immediately what happens? The restoring force develops here. That is, I'd say this is F3, and the distance is L by 2, and small displacement is X double dash. So that force F3 is equal to minus 2kx, that is equal to minus 2k. What is the x? L by 2 into theta. L by 2 into theta. This is the force. Then torque is equal to force into perpendicular distance from the axis of rotation to the point of application of force. So that is L by 2. So this is 2k L by 2 into theta into L by 2. So 1 2 will cancel. So this tau 3 is equal to, how much I got? Minus k L square theta by 2. This is what we got. So now tau is equal to I alpha. So I alpha is nothing but the tau. So I formula we know na, because this is the fulcrum is at the one end of the rod. So one end of the rod, the axis of rotation is passing through one end of the rod, then moment of inertia is ml square by 3. So I will write here ml square by 3 into alpha is equal to minus k L square by 2 into theta. Like that I will write. So L square cancels. Then alpha is equal to this 3 will go like this, minus k by m 3 by 2 into theta. This is equation 6. So this equation I will compare with alpha is equal to minus omega square theta. This is a SHM equation. Angular acceleration alpha is equal to. So from comparing these two, omega 2, this is the frequency of the in the second case, second diagram, right? That's why omega 2 I given. So root will come, root 3k by 2m. This will come. This is the 7. What we've been asked, we have been asked to find f1 by, therefore f1 by f2 is equal to omega 1 by omega 2. Omega 1 is equal to how much? Root of 15k by m, 4m into, this is reciprocal I have to take, 2m by 3k. So here k cancels, 3 ones, 3 5s. So therefore f1 by f2 is equal to under root 5 is there, and under root 2 ones, 2 2s. So 5 by 2 will be there in the root. So this is our correct answer, 5 by 2. So let us look for the answer. For the problem number 3, C is the correct answer.